Hello and welcome to the Edexcel Further Maths videos for Mechanics 1. This is the elastic springs and strings section, and this is 1.3 problems using conservation of energy. So if we have no non-conservative forces doing work, that's things for example like friction or air resistance, then energy is conserved, and we have that our final kinetic energy plus our gravitational potential energy plus our elastic potential energy is equal to our initial kinetic energy plus gravitational potential energy plus elastic potential energy. We will look at questions where we have some non-conservative forces that are doing work in our next video. If we do have other forces doing work, we can still use the same ideas as in earlier problems, but in these problems we're going to now need to use our elastic potential energy as well as kinetic energy and gravitational potential energy in the work energy equations that we've seen in previous videos. So let's have a look at an example now. We have an object of mass 5 kilograms and it's attached to an end of an elastic string, natural length 4 meters and modulus of elasticity 150 newtons. The other end of the string is attached to this fixed point O. We hold the object here and then release it from rest. What we're interested in doing is finding the lowest point reached by the object in that motion. Now in this particular case you can see that acceleration is not constant. We're going to reach a point, if you imagine a bungee jumper, where we reach the end of the natural length of that string, and then the acceleration is going to be affected by the fact that we're now stretching it. So we can't use that. Now we could use Newton's second law to solve this problem, but it will be quite involved. And actually, it's really good to get into the habit of using some energy methods because we can solve a lot of quite complex problems using these. So what we're interested in is thinking about what's happening initially and then what's happening at the end, because we know due to conservation of energy that the sum of these things should be the same. So our initial kinetic energy is 0. Our initial gravitational potential energy is mgh. And our elastic potential energy is 0. Now if we think about our string here, we have our natural length of the string, which is 4, and then we have the extension in the string, which is x, and h is 4 plus x. Okay, so at the lowest point, our kinetic energy is 0 because we're not moving anymore. Our gravitational potential energy is 0. We don't have any of that left. We've travelled that whole h distance. And our elastic potential energy is lambda x squared over 2L, which we learned in the last video. So that means our elastic potential energy is 150 times by h minus 4 squared, because that's the extension in the string. H is the lowest point we've reached, and the difference between that and the natural length of the string is the extension, and that's divided by 8, which is 2 times the natural length of our string. So now what we can say is that our initial energy, mgh, needs to be equal to our final energy, which is 150 h minus 4 squared over 8. We know that h is 5, so we have 5gh is 150 h minus 4 squared over 8. Now if we expand this all out, we end up with a quadratic, which is 150h squared minus 1592h plus 2400 equals 0. Now at this point you would solve this using your graphical calculator or your scientific calculator, and we would end up with 2 possible values for h. Now we've discarded this value here because actually that would mean that we were at a higher point than the natural length of the string, so we know that the height we reach, or the distance away from the starting point, must be 8.79 metres. So our lowest point is 8.79 metres below our starting point. Okay, so on to example 2. Here our object has a mass of 0.5 kilograms and it's attached to the end of a light spring, natural length 40 centimetres. So L is 0.4 and lambda is 180. We're now going to pull it along, so we've got our natural length here of 0.4 and we're going to get to a distance of 50 centimetres. So our extension is 10 centimetres or 0.1 metres. The object is then released and we want to calculate its speed when it reaches O. So we've got L is 0.4, lambda is 180, x is 0.1. Our elastic potential energy, and that is lambda x squared over 2L, which we learned in our previous video. So that is 180 times 0.1 squared over 2 times 0.4. So our elastic potential energy is 2.25. Now, we know from conservation of energy that the energy, our final energy, must be equal to our initial energy, and this elastic potential energy, once we let go of the object, is going to be converted into kinetic energy. So we know that kinetic energy is a half mv squared, and we're going to have all of this elastic potential energy being converted into kinetic energy because we've got a smooth table. So 2.25 is equal to a half times 0.5 times our speed squared. So we end up with a speed of 3 meters per second. Okay, thank you for watching our video 1.3 problems using conservation of energy. The next video will be 1.4 problems using the work energy principle.